This is a question taken from 2015 Harvard MIT math tournament. Now, we have polynomial equation, and we want to find R1 square plus R2 square up to Rn square. And those R's are real roots. We know that there's 8 roots in this equation, but we don't know how many of them are real roots. So this makes questions a little complex, and we don't know how many roots are real. So let's factorize this polynomial. So we try to find the nature of the roots. Now this polynomial can be written as x8 plus 2x fourth minus 16x fourth minus 8x cubed minus x squared plus 1 equal to 0. And this one, and that one form a perfect square, x fourth plus 1 squared, right? This one becomes this, and that. And for the remaining, we'll take common factor out. This will be 16x squared minus 8x plus 1. Then this is x fourth plus 1 square. This is a perfect square again. This is a 4x plus 1 square, right? Then we combine these two, becomes x to the fourth plus 1 square minus 4x square plus x square. Then we can use the difference of the square, becomes this plus this, which is equal to x fourth plus this plus 1. Multiply this minus that. This is x fourth minus 4x squared minus x plus 1. This minus this times this plus this is this. Now we can analyze better the roots. This equation has 8 roots. 4 roots are there, 4 roots are there. For this one, we know that this is always positive if x is a real. And for this one, this is a parabola, right? Look like this one, because the leading coefficient is a positive. So the curve like this. The first derivative is 8x plus 1. If this one equals 0, then at x equals to 1/8, right? So this minimum point is at x equals -8. You put a -8 there, you calculate this positive, this axis, right? In other words, this quadratic will never be 0. This is always positive. Therefore, together, this one is not 0 unless x is a complex number. So, in other words, this one has no real roots, because this one's never be negative. This never be negative. The summation is always positive. So now we have a better picture. This 8 roots, 4 of them are complex. If we have a real roots, must be there. So we analyze this polynomial. Okay. Now the picture is a little better. So we analyze this x fourth minus 4x squared minus x plus 1. This equation, if they have real roots, must be there. But we're still not sure that these 4 roots are, well, how many of these 4 roots are real? Now then we need a further analyzing. Now, let me do this one. If this is f of x, then f prime of x is equal to 4x cubed minus 8x minus 1. Right? F double prime is equal to 12x squared minus 8. If this one equal to 0, which means that x is equal to positive or negative square root 2 over 3, which means that this quadratic, this polynomial, it has 2 points of inflection. See? It goes like the 2-point inflection. Because the leading term is positive. Therefore, when x is big, the function value is big. When x is a negative, very large negative, it is still positive, right? Because the leading term is positive. But we know that there are two points of inflection, which are symmetric to the. Let me sketch it this way, because a picture worth 1,000 words, right? This point is a negative. This point is 2 over 3 square root, and at 0. At 0, function value is 1, right? So this is a 1, 0, 1. Now, why we do this? Let me show. Let me explain it. Okay, this is a 4th degree polynomial. The picture look like this, right? Both are positive infinitive when x is positive infinity or negative infinity. Now, how many are real roots? It depends the location of the curve, right? If this is the x-axis, this polynomial has no real roots. If this is the x-axis, then there are 2 repeated roots are real, 2 complex roots. If the axis is there are 4 real roots. If the x-axis is there, the 2 real roots, 2 complex. So we just want determine that the x-axis, where the x-axis located, it will determine how many real roots, right? Now, how we do this? Well, this is my way, okay? I believe there's other ways. Now, let me do this. Okay, we know that these are points inflections. Therefore, the maximum point must be between them, between these two, because these 2 points are symmetric with respect to x-axis. When x equal to 0, y is equal to 1. So 0, 1 is a point on the curve. But we know that the maximum must between this and that may not necessarily be on 0, right? But I know that the maximum point must be higher than 1. Therefore, the maximum point must be above the x-axis. Okay? Now then, we analyze, say, this point. We know that f prime of 1, we just simply plug the value here, right? You get a -3. And f prime of 2, we plug it there, we get 17, which is positive. Therefore, this point, which is a minimum, right, must happen between 1 and 2. I hope you follow me. The minimum point must be between 1 and 2 because the derivative function is f prime, right? And then we check f over 1. F over 1 is -3. Just plug 1 here. And f over 2 is -1. We just put 2 there, okay? These two values are below x-axis, below the x-axis. Therefore, the minimum value for sure will be below x-axis. All right? This point must be between x-axis. This point must be happening in the interval of 1, 2, because f1, f2 are negative. Now, for this point, now we know that this is a point of inflection. Therefore, the minimum point must be less than this. Right? Let's check f prime -1. We just plug this one here, right? Yeah. No. I'm sorry. We check this f of a -1. We want to check whether the point is below or above x-axis. This one we check, put a 1 here, -1 here, is a good -1. Which means that the function value after -1 at -1 is negative. But minimum point is what? The minimum point, f prime -1 is a 5. F prime of -2 is -15. From these two, I know that this point is between -1 and -2. Okay. The minimum point must happen at the x value between these two. Also, we know that at this point, at -1, the function value is already below x-axis, below x-axis. Therefore, the minimum point must be below x-axis. This point must be below x-axis. This is also below x-axis as we did it before. This is above. Therefore, my x-axis must be there. This is my x-axis. 1 is above, 2 below. That from the previous analyzation. Therefore, we have four roots real. We have 4 real roots. In other words, where is my? Yeah. Where's my yeah. Therefore, my 8 roots, these are 4 complex roots. These are 4 real roots. As we analyzed, right? As we analyzed here, because this is the curve and this is above, this is 2 below x-axis. Therefore, we have 4 real roots. Yeah, that is just one way of analyzing. Now, then the picture is clearer. We have only this, right, x fourth. Now we know that 4 roots are there. Real 4, they are all reals. And this equation we can write x fourth plus 0x cubed minus 4x squared minus x plus 1 equal to 0, right? Then we have 4 roots. We know that these 4 roots are real. Using that relation between roots and the coefficients, we know that. Then we know that R1 plus R2 plus R3 plus R4 is equal to negative 0 over 1, right? And R1, R2 plus R1, R3 plus R1, R4 plus R2, R3 plus R2, R4 plus R3, R4 is equal to this over 1, right? Is equal to negative 4 over 1. One, two, three, four, five, 6, yes. And since R1 plus R2 plus R3 plus R4 square is equal to R1 plus R2 plus R3 plus R4 squares plus 2 R1 R2 plus R1 R3 plus R1 R4 plus R2 R3 plus R2 R4 plus R3 R4. Now simply the expansion of this by this bracket, and this means that this is a 0, right? We have analyzed this 0 square is equal to R1 plus R2 plus R3 plus R4 squares plus 2 times this. This is negative 4. Therefore, R1 squared plus R2 squared plus R3 squared plus R4 squared is equal to 8. That is what we're looking for. Okay. Thank you for your watching.